start with tensors, okay? And as I said, tensors is not something which you come across on a daily basis. But then in general, there is this notion that if you represent something in a matrix form, you are usually representing tensors. That's actually not correct. Tensors and metrics are totally different things, okay? Matrix is just a mathematical tool to represent something, okay? And it can represent different mathematical, components and all. But then tensor is also one of the component that can be represented by matrix in a way, but then there are different types of matrices. Like you can represent a tensor in 3-dimensional form, 4-dimensional form, okay, and that takes a different thing altogether. So before we start with what are tensors, okay, I'll just give you something here which you might have come across. There is something which we will always start with when we talk about vectors and all, is nothing but scalars. So scalars are basically, 0-dimension tensors. So these are usually scalars. And then we talk about vectors, and this is basically having a 1-dimension tensors. So these are actually called vectors, okay? So if you have anything like a 2-dimensional representation or a 3-dimensional representation, these are something which we usually call them as tensors, okay? So we are going to look into the definition and the idea of tensors, okay? This is what is the aim of this particular unit is. And before we start, let's take certain important formulas that we already know and see what exactly do they represent, because we know that they are actually being represented by vectors, but it's not the case. This can be represented by tensors as well, okay? So let's just have a look. Let's say I'll take up certain formulas, okay? Let's say we know this L is equal to I omega, right? Angular momentum, okay? So momentum is mass into velocity, so this is moment of inertia into the angular velocity. This is the angular momentum. This is one formula that we know. Let me take one more. J is equal to sigma E. This is something which is there, you might have studied in, when we talked about electric field and current density and so on, okay? Even in your undergraduation you might have done it. And then you can have something like I is equal to mu into H, okay? So if you look into these quantities, which quantities I'm talking about here are these I, or maybe sigma, okay, or maybe mu, okay? So these quantities that we actually have, okay, or I can just BH, B is equal to mu H, let's say, okay? So these are the quantities which are basically vectors, okay? So if we just look into the definition of these quantities, they always will represent a vector because they do have a direction and magnitude, okay? These are not scalars, these are vectors, and these vectors are something which are there in isotropic medium, and that's the difference here, okay? This is very important to understand. So we already know what do you mean by isotropic. So you have a property which is actually similar in all directions, okay? So if you are in a 3-dimensional space, okay, and you observe that the property or the behavior is same in all direction, you say that it is more or less an isotropic medium, okay? So if you're standing somewhere, you have the same amount of air surrounding you, you are basically in an isotropic space, okay? You have a gas, okay, one single type of gas which is enclosed within a chamber. Within that system it will be more or less an isotropic system, but it's not the case in reality. A lot of time it does happen that it may not be isotropic. The property, the behavior will be different in different directions, okay? And there is something where we use tensors. So when we talk about these I, sigma and mu, these may be vectors in isotropic medium, but these three quantities would be actually tensors, okay, in n isotropic medium. So if you consider n isotropic medium, we are basically looking into tensors, Okay, and you will see that tensors are something which will actually start in second order. Okay, so these are all, you can say, in general I can say that if I don't write down dimensions, dimensions may not be the right word here. Let me just write down this as order. Okay, dimension is not the right word, sorry. So I think I should write it down as order. So what happens is you have vectors, okay, and they might be of first order, and that will actually represent tensor. They may be in a 3D space, but still it will represent a vector. So if you basically have an x-axis, okay, a y-axis and a z-axis, and you have a certain object, let's say it is moving with a velocity v, making certain angle with the x, y and z axis. They are in a three-dimensional space, but it is having only one order. Okay, and that is how the vector is represented. Now what do I exactly mean by vector having one order? It means something like this. Let's say I have this velocity, okay, which is actually a vector, and it's being represented by, let's say, 2 meters along the I direction, plus let's say 3 meters along the z direction, plus let's say 1 meter along the z direction. So these I, j and k, okay, these I, j and k actually are something which represents the basis vectors. So along with a direction, that means let's say along the x direction, this is the component that we have. Okay, it is being represented by only one basis vector, and that one basis vector is this one that we have here. So this one in the example that I have shown is the basis vector that we are talking about. It's in three-dimensional space, but along with each component there is only one basis vector that is associated, and this is what is vector is all about. But there may be a case that along with each component there are two basis vectors which are connected. There are three basis vectors which are connected, and as a result this won't be a vector anymore, this will be a scalar. So if you represent only a scalar quantity, let's say velocity, and let me not mention velocity, maybe I can mention speed here because velocity is the vector. So if I represent something like speed, okay, just remember this, okay, if I represent something like, let's say, speed, and I can mention it to be 2 meter per second. So you see, it does not have any basis vector. No basis vector is associated with it. Tensor is a very complicated concept later, but initially if you get the basics, I think it should be easy for all of us. Okay, no basis vectors associated. Okay, that means zero order. That means it's a scalar. So zero basis vector, no basis vector, zero order, scalar. You have got one basis vector associated with it, it will represent a vector. Just understand this. But then if there are more basis vectors associated with the component, we usually tell them as tensors. So that's very important. Okay, although the velocity, the speed, as well as these components in isotropic medium, all of them may be in a three-dimensional space. All of them may be in a three-dimensional space. Okay, so if you look into this particular example of vectors, okay, you see that it is in a three-dimensional space, and the basis vector associated with each component is just one. So that means it has basically got three components. See, it has got three components. Here you're basically having, maybe it's in three-dimensional space, no problem, but then it has got zero basis vector associated with it. That means it will be having just one component. This is the component that we have. So in a similar way, if we talk about tensors, there are always chances. Okay, let me just write down this tensors. There are chances that it will be in three-dimensional space, no issues, but then they might be having two basis vectors associated with each component, and as a result it will basically have 9 components. Okay, 3 square, which is equal to 9. So this is important. Okay, you will get the hang of it slowly. We are going to do some examples. Okay, we will to discuss it in detail later. There might be a chance that you will have three components, and then it will be basically 27. Okay, three basis vector associated, so there will be 27. Okay, so that's always the case. So what happens is, usually when we actually represent a tensor, we may represent it something like this. Okay, so let's say you have got a bar or maybe a box. Okay, and you are applying some kind of stress to it. So you remember Hooke's law, we do have stress and
Hello,
strain
sir.
there. Yeah.
Sir, can you please describe the isotropic medium and anisotropic medium?
Okay, so let's say you basically have got a cylinder somewhere. Okay, maybe I will have a cylinder here, and you have got some kind of gas in it. So let's say it's an LPG cylinder. You have got your liquefied petroleum gas inside. Now think about a property, anything, let's say density. So if you are within this box, the density, whether you go in this direction or you go in this direction, okay, or you go in this direction, okay, this direction, this direction, this direction, in all the direction, this property will remain the same. The density is not going to change. It will be equally distributed within the cylinder, and that is something which is actually called an isotropic medium. Okay, but in general there are a lot of cases where the property might not be the same. So if I take this example of a box, and if you are applying some kind of pressure along this direction, some kind of force along this direction, this box is going to get deformed here. This is box is going to get deformed. Now in case the box gets deformed, okay, the let's say now the property that I want to measure is the pressure or the force or the stress that the box is experiencing. Now the stress that the box experiences at this particular point will be different from the stress that the box experiences at this particular point. So in a way we can say that this is actually an example of an isotropic medium. In a way we can also say that, say you are standing somewhere, okay, and it's totally normal weather, okay, no, nothing windy is there, you're just standing there. You feel that whichever direction you turn, it will be basically more or less isotropic in nature. Okay, the behavior will be more or less isotropic in nature. But then let's say there is a storm which is coming, so that means behind you might be the weather is normal, but in front of you the wind speed is extreme. So that means that is not an isotropic medium, that is an anisotropic medium. That is an anisotropic medium. Okay, so you have to understand that isotropic medium and anisotropic medium, if you consider any kind of property, maybe the density, maybe the velocity, maybe the stress of the strain, it won't remain same in all the directions, and that will separate the isotropic from the anisotropic medium. Now why are tensors important in real life? Because in general whenever we talk in physics, most of the times we are considering something which is an idealized case. In fact, if you are doing any kind of experiment in the lab, okay, let's say you are making some kind of design, okay, you are doing it in ideal condition. Let's say a solar cell, okay, the solar cell, this is an ideal condition that you will have maximum sunlight, okay, and based on that the specification of the solar device will be given. But that's not the real case. If you go into the real world, you will see that it's not as ideal. It might not be having maximum sunlight. Someday it might be cloudy, someday it might be windy, someday the intensity of the sun might be less because of this cloudy weather and so on. So that's not an ideal condition. Okay, so the point here is that when you come into the real world, most of these things, there will be a lot of things which will be anisotropic in nature and not isotropic. And if we want to represent such quantities, we cannot have something which we call as a vector or a scalar. We also need to take help from tensors, and that's the basic aim. Okay, when you study in your class 9, 10, you basically don't study vectors much, you just have an idea. When you go to 11, 12, you realize that no, not only magnitude, I need to understand direction also, and then you keep using on vectors. When you go to your graduation, you will see that third year, maybe when you're doing your major paper, maybe they'll introduce tensors. Okay, and now is the stage when you want to understand tensors better and want to know that why exactly are we going to use tensors in the real world. Okay, so this first slide is only to help you understand what are tensors. Okay, and for this we need to remember certain things. First thing is, it may be in three dimension every time, maybe a vector, maybe a scalar, maybe a tensor, doesn't make a difference. The important part is how many directions are we assigning, how many basis vectors are associated with it. So if it's a vector, there are only one basis vector associated with each component. If it's a scalar, we have got zero basis vector associated. So that means it will be just be a one dimension or one of first order tensor. But if you are considering anything higher than the first order, it is always a tensor. Now the question is it always three dimensional? The answer is yes, most of the times. But sometimes what happens is, you might be representing time, okay, as the fourth dimension. So when we talk about relativistic assumptions, relativistic relations, there if we want to represent something with a tensor, we'll bring in the fourth dimension. But here I'll restrict ourselves to a three-dimensional system. So that means it will always be 3 square, okay, 3 cubed and so on. So you might have change in the number of basis vectors, but the dimension more or less we'll try to consider only a three-dimensional system. So if you're using any, doing any kind of research, okay, and if you want to understand the effect of all these components of a particular system, you have to use a tensor system. And there basically you use, nowadays you use computer programs and all to do your calculations. It will take time, but definitely we can actually use that to do such calculations. Okay, so let's try to understand certain things which will be related with the mathematical development of the mathematical idea of tensors. Okay, and one of them is Kronecker delta, which you might have done a number of times. Okay, so let me just write down KRO, okay, Kronecker delta. So Kronecker delta function is actually something which you might have used every now and then, and we are going to use it in tensor also. Okay, this is important. So in order to understand this, let's just consider certain situation. Let's say we have got two frames of reference. We're basically going to use two frames of reference. Okay, how we consider it, how we represent it is totally our choice. Let's say one is the S frame of reference. Okay, and maybe the components are x1, x2, x3 and so on. We can have another frame of reference, might be the S dash frame. So when we talk about tensors, okay, we also need to know the transformation matrix. That means that if we want to go from one frame of reference to another frame of reference, how the tensor will behave, that is also something which we need to represent. So in this frame, we may represent it as, let's say, x bar 1, x bar 2, x bar 3 and so on. Okay, so these are two frames of reference that we have, and any of the component of this frame might be, let's say, xi, and here it might be, let's say, xi bar. Whenever I write down the bar, maybe I am representing the primed set of coordinates. Okay, so here this Kronecker delta, although we are going to use it later, delta is represented as this Kronecker delta, delta ij. So as I told you, there are two, okay, orders. That means it is more or less representing a tensor. I and j both are there here, okay, in this particular expression. This will actually be 0. We are going to use it later. If I is not equal to j, and this is going to be 1 if I is equal to j. Okay, and there is a way to represent this, something like this: delta ij is equal to delta of xi, whatever is there on top, I'll write it down, this, divided by delta xj. So if I is equal to j, this will become delta xi divided by delta xi, so obviously it will be 1, else it will be 0. Okay, so this is something which we are going to use. This is the definition of Kronecker delta, which you might have studied before. Now let's just go back and check different kinds of tensors. There are tensors which can be represented in different ways. It depends on what component are you representing, and that's why there are different ways of representing these tensors. Okay, so let me just write down these. Okay, so if we talk about tensors, and we are going to take one by one. Okay, each of them we are going to take it one by one. So there are four tensors that we need to know. Okay, we're going to look into that application part and everything else later. So 1, 2, 3, and maybe 4. So the first kind of tensor is called a contravariant tensor. Contravariant. The second is, you might have guessed, covariant tensor. There are certain properties which you also need to study. Then there is called the mixed tensor. You can understand this also. This is actually, this, okay, I'll come to that later. Let me just write down all these four first. Invariant. So there is no variation, we call it as invariant tensors. So there are four kinds of tensors, okay, and let's say if I represent this as 1, represent this as 2, this mixed tensor would be 1 plus 2. If we mix, we have a mixture of contravariant and covariant tensor, this will be the mixed tensor. Let's represent it as 3 and let's write this as 4. So these are the four kinds of tensors that we have, okay, and we are going to just look into each of them one by one, okay. So there are different components. So whenever I write down a vector, let's say velocity is equal to 2i, 2 is the component, we already know it, okay. So in a similar way we can actually represent and take the components of tensors also, and how we transform from one system, let's say S to S prime, or from S prime to S is actually is a part of your syllabus, transformation equation, or how we transform from one system to another. When we are you're going to go more deep into quantum mechanics, probably these transformations you are going to use as well, okay. So let's just represent this again. Maybe I've already done it. So S and S prime are there, okay, and let's say I will represent these, okay. Let me just write down this here. So this is x1, x2, x3 and so on, and any of these representations may be represented as xi. And if we just look into the components of these, okay, maybe I can represent it as a1. It's not mandatory you should write it down this way, but usually we can do it this way, a3. These are all the components of these vectors, and any of these component may be ai. Okay, let's take this one representation. In another frame of reference, okay, the system is x bar 1, x bar 2, x bar 3. I'm taking a general case, okay, so don't get confused here. And this frame, any component may be represented as x bar I, and the component may be a bar 1, a bar 2, a bar 3, and this is a bar I. Okay, so that's how we take it, okay. I'm just taking the components separately, and if you want to go from one system of transformation to another, that means from the prime frame to the unprime frame, or unprime frame to the prime frame, we can do it. We have got a relation from the prime to the unprime. So a bar I, if I write down, that means I am in the S dash system, and this is written as del, there will be a mention of canonical delta here, del x I bar. So there is an I bar here, so we'll just write down that I bar divided by del x j. Okay, so it's basically a partial derivative, because you know that this can be a function of different x's, okay, x1, x2, x3 and so on. So if I take this xj and aj, Okay, and if I just want to represent this, you know that this is in the S prime frame and this is in the S frame. Okay, this is in the S prime frame and this is in the S frame, and there is a reason why we have put a superscript to it and not a subscript. This is put an I, this is J. These kind of representations where we actually put the I and the J and the K's on the superscript is actually a representation of contravariant tenses. These are contravariant tenses. Okay, so try to understand this. I'm going a bit slow because this is not a conventional topic. Okay, so these are contravariant tensors where we represented it with a superscript and not a subscript. If it's a subscript, we will be actually representing a covariant tensors. Okay, so if I say that I can have a transformation from S dash to S, that means the reverse should also be possible. That means I should also be able to write it down in terms of S in terms of S dash and not S dash in terms of S. Okay, so we are going to just look into that transformation right now. So let me take a new slide. So let's just have a look into the transformation. Okay, so maybe I can just write it down. This is actually an important question. I've seen normally standard questions I can ask you to transform from one system to another, or even in entrance exams and all also they do ask it and give you as multiple choice question. So what I had is this: a bar I is equal to del xi bar. Just this is just a way to represent tensors. Okay, that's it, don't get confused. This is just a standard way and that's why we are representing it this way. Don't scratch your head much that why we are writing it this way. This is just a way to represent, that's it. Aj. So this is what we have written in the previous slide. So whenever you have this, you just put the same component here also. I bar is always there. Okay, so for transformation what we do is we are going to multiply with, let's say I have got one more component k divided by del xi bar. So I multiplied with this. I'm going to multiply the same on the other side. Why? Because you see, you cannot go from one set of coordinate to another set of coordinate just by cross multiplying. That's not the standard procedure. Why? Because in vectors also we know that the order is very important. Here also we have to go step by step, follow the sequence one after the other. We cannot just simply cross multiply and get our results, right? In vectors also we do know that A cross B and B cross A are not the same. So in a similar way, here also we have to follow certain rules and steps. So what we do is, if you want to cross multiply this, this will go here and this will come at the denominator. So that's why we are taking another component del x to the power k divided by del x bar I. Okay, and if you are multiplying with this on the other side also, we should multiply with a similar quantity. So maybe I can multiply this del x bar I del xj. We'll keep it like this. You'll see we are going to use Kronecker delta here. Okay, so don't worry. And what I've added is this del xk divided by del xi bar. Okay, into aj. Aj will remain as aj. So you see, you can actually just cancel this out. Okay, these two can be cancelled out. So maybe you can just show it here. So if I just write it down this way, this is equal to del xk divided by del xj into aj. Okay, now we know the definition of Kronecker delta, right? So if we just go to the definition of Kronecker delta, we know that del of kj, ij, kj, it depends on what is the component that you are considering. If you're taking k on top, I will write it down as del x to the power k divided by del x j, superscript. Okay, let me not say to the power, and this will be equal to 0 if I is not equal to j is equal to 1 if, or not I, we have got j and k, sorry, no, I is not here. So if j is not equal to k is equal to 1 if j is equal to k. Okay, so let's try using this. So therefore this aj, okay, let's take this aj on the left hand side. So I'll write it down as aj, and you see del xk del xj, del xk del xj is nothing but the Kronecker delta. So I can directly write down this as Kronecker delta kj. If j was on top, k was at the bottom, I would have written it as jk. Okay, that is the representation, don't get confused here, is equal to del xk divided by del xi bar into a bar I, or ai bar. That's it. Okay, now we are saying that this is k, right? So okay, let me write it here. So when j equal to k, j equal to k, so I can just write it down as ak is equal to, because delta k k, if j is equal to k, this is equal to 1, so this Kronecker delta will become 1, so it will be 1, nothing changes, and we have got it as delta xk divided by delta x bar I into a bar I. That's the transformation equation. That's your transformation equation. Okay, so you see, you have gone from a bar I aj to ak a bar I. You have just introduced one more component, which is k. Okay, one more basis vector we can say, which is k. Transformation will remain the same. So this is how you go from a primed, this was from prime to unprime, we are going from unprime to prime. So we have to use this technique. So this is how we transform from one system to another. This is how we write down the transformation equation, and this is for contravariant. And in similar way we can also do it for covariant. Okay, we can also do it for covariant tensor. So I was talking about order here. Okay, so you know, it basically has got how many components. Now someone asks you that how many components does this tensor have, so you can just simply write it down. It's in mostly in 3-dimensional space. Okay, so we are considering a 3-dimensional space here. So it is 3-dimensional space. We have got just, you know, one basis vector which is k. Maybe this is only one basis vector which is I. So there is only one basis vector associated with the component. So that means this is 3 to the power 1. That means, you know, this is 3 components. It will basically have 3 components. Let's just talk about second order contravariant tensors. Okay, since we are talking about the first order, second order contravariant tensor. What happens here? We basically have it as a bar, and we are going to write it down as ij. Okay, depends on how many components it will have. Okay, so ij, so that means I and j both are on top. So how I represent it is this: del xi bar. You can check here, we have done it in a similar way, but then we have got j also, so I'll just write it down as del xj bar. Okay, and what about the denominator? Okay, if we basically have j here, we are writing down j here. Okay, we are going from one system to another system. Maybe I can represent you know, tensor on the other coordinate system, and maybe I will take a different set of values, let's say p and q, because I and j I have already used here, and you know, if this is I, this is j, so this is different. Here if I write down I can write down p here. If I write down p here, this will be with respect to x to the power p. So here also I've written it as P and Q, so I can write it down as del XP del xq. So the most confusing part in tensor is how to represent them. Okay, so that's why I'm just making it clear. I've written ij here. The corresponding component in the unprimed system is p and q. So here we are going to differentiate partial differentiation with respect to x, superscript p, and x superscript q, and this I and j will remain here. This is how you represent it. So this is basically a two-dimensional tensor. Okay, so basically we talk about this as number of component is equal to 3 square is equal to 9. So when we are studying the chapter of tensors, even vectors we are going to call them tensors. Okay, but we know that vectors are basically tensors with this one as 1, right? The component, the basis vector is 1. Okay, but we are going to just talk about tensors here. We're not going to talk about vectors again and again. So if we have written the second order, I think even the third order we deserve to write it. So let's just write down the third order. This is a one-time understanding. Okay, we're going to use it probably later. Let's talk about the third order. Okay, third order contravariant tensor. Let me not write it down. So third order means you will basically write it down as a bar n I j k. How you represent it? Remember this technique that I am doing. Okay, write it down in a similar sequence. You are never going to make a mistake. Otherwise, it's a bit confusing. Even I get confused sometimes. So del xi bar and then del xj bar. Why bar? Because we are talking about this a bar here into del xk bar. Done. What about the component here? I have represented it with pq. So let me just give the same notation. Let me write it down as pq r. Once I write down this, now this is easy. Del xp. Don't write it down in the subscript because we are representing a contravariant tensor. As soon as you write down in the subscript, we are talking about a covariant tensor. Del x r. This is in this. Okay, so here also if we just want to find out the number of components, we basically have it as 3, and there are 3 basis vector I, j and k with each component, so that means it is 3 cube. So this would be 27. So that's how you actually do the transformation, represent the tensors and so on. Okay, so it's important because it's a bit confusing, but then once we look into these representations, we understand them, I think it will become a bit easy. Okay, so if I've talked about contravariant tensors, let me take one more. Okay, for today's class, covariant tensors. Okay, covariant tensors is also important. So let's talk about covariant tensors. So I already told you how to represent them. This is the second one, and representation is this. You write down a bar, but then you don't write down I at the subscript, you write it down at the superscript. Okay, so I hope you know superscript you write it at the bottom, subscript you write it at the top, and then in a similar way we can actually have it. So let me just show you the difference once. Let me just go back to the previous page. So you see, you have bar I and it is on the top, but when we are talking about covariant tensors, we have got the bar and the I at the bottom. So we were going to write it down as this, del x bar. This will remain as I because this is power. Okay, please remember this is del xp. This is representing a covariant tensor, but this representation, this will always remain at the power. Okay, order of differentiation, partial differentiation, but then the bar I will come at the denominator, and that without the bar in the unprimed frame it will go at the numerator. So you have to practice it once or twice, and then I think it should be okay, and then we can just represent this. So I will write down this as a subscript p, because we are talking about covariant tensors. So when we represent contravariant tensors or covariant tensors, this component which I am representing by a, that will have a subscript of I, subscript of p, and so on. Okay, not the partial differentiation part. That will change depending on whether it is contravariant or covariant. It will go in the numerator and this will come in the denominator, but then this writing representation won't change for this. It will only change for the tensors that we are actually representing. Okay, so that's very important. So in a way, if I say that I have got an S frame, I will basically have the function components, right? So this is x1, x2, x3, and so on. Okay, but then if I have the function component, that means I'm representing the the functions. Okay, it may be a combination of number of functions. These functions are nothing but the tensors. So it will be a1, a2, an. No confusion here. Okay, so if I'm saying that L is equal to I omega, this I actually defines this. Okay, and this I, which is actually the moment of inertia, may be a function of x, y, z, and so on. Okay, I don't know what kind of structure we are considering. Maybe it's a box, it's a cube, it's a sphere, and so on. Okay, maybe a three-dimensional space. So I need to consider all these. Okay, so this is basically a function of, again, x, y, and z. So this is also representing those functions. Okay, if we just take this example, so that means this is actually represented by this. So if you write down at the subscript, these are all covariant tensors, not these. Okay, these are not tensors. These are not tensors. These are tensors. Okay, so let's not get confused here. Okay, then we can actually talk about the S prime. So same thing. Okay, x bar 1, x bar 2, x bar 3. And then if we just want to represent this, this would be a1 bar, a2 bar, and this would be an bar. Okay, so that's it. So now if I just want to do the transformation, we can again do it in a similar way. We can just write it down as ai bar into, now I want to do the transformation. So if I think about this, I can take it this way. I can take it here and I can bring it here. Okay, and I have to multiply a similar component, but this p won't remain p, this will become k, right? I'll take a different component here. So this would be del x bar I divided by del x k is equal to del x p by del x I bar is the same into this one I have done. So I'll operate with this on this side also. Okay, so in a way we can say that we are doing mathematical operations. Okay, and mathematical operations, we need to maintain the order, we need to follow certain rules, and that's very important. Into a p. So we can see that I think you got this from the last problem. We solved this is done. Okay, and then we can actually use the Kronecker delta thing. So this is del x bar I divided by del x k. Let me take it on the other side, and this side I can just write it down as ap and this will, so see this k, please don't write this down again, pk. It was kj, so I've written delta kj, delta xk, delta xj. It is delta xp, delta xk, so it will write down delta pk, right? So it's just a way to write it down. That's it. You remember it, to write it down. pk, Kronecker delta, is equal to the other side. So other side is a bar I into not delta, sorry, Kronecker delta तो लिख दिया हमने already. So we are going to write it down as delta x, sorry, I bar. Don't write down, never write down this I with the subscript or, and you replace this with x divided by delta xk. Okay, and then as I told, when p is equal to k, we did it in the last problem. When p is equal to k, this is 1, so that means we have transformed ap is equal to This will be a 2 marks question. Okay, chances are it will be there. Bar divided by delta x k into a I bar. Okay, and that's the transformation equation. So to remember this transformation equation, the first one, and then if you remember this, you can actually do it. Okay, you can easily transform from one system to another. Okay, please remember this is x bar I by xk. If I write down xp here, you take it on the other side, you see that everything gets cancelled out. You're not really doing a transformation here. Okay, so that's not the transformation. You are going from one basis vector to another basis vector, because you're transforming from the s frame to the s prime frame. Okay, so try to sleep over it, try to just get the hang of it. Okay, I know it's not something which you can all of a sudden you will get it clear in your head. It will take some time, and I suggest that you take that time and try to understand it better. Okay, so it's in three-dimensional space, so the number of components is obviously 3 to the power 1, which is 3 components. Try writing down the second order and the third order on your own. Okay, it's not complicated. If you just take it this, maybe I'll take this and write down the second order. It will be ij. Okay, so del x bar I, del x bar j, and on top it may be del xp, del xr, a, pq, right? Okay, anyway, let me just write it down only, otherwise you might miss it. It's very important. So it's not complicated. If you want to write down the second order also, it's very simple. I have to just write it down as a bar. Second order means basis vector will be 2 I and j, and then I can just write down the denominator here. It's covariant, so x bar I into denominator x bar j, and this is so I'll write it down as a pq. So this will be del xp, del xq. That's it. Now imagine you want to do a numerical problem based on this. Okay, I'll just tell you a simple idea here. Suppose you want to do a numerical on this, it's going to be very troublesome. Okay, you don't know what is the value of p, what is the value of q. Maybe it's 4, maybe this is 5. Okay, so in that way, it becomes a very complicated problem. So if you go to the tensors, okay, which are having so many components, okay, for this it's 9 components, 3 square, which is 9 components. The calculation becomes very complicated, and that's why when you actually use programs like MATLAB and all, okay, you are already you will be doing your numerical analysis. They are probably only tackling tensors, but then a program like MATLAB can be actually used to solve such problems. Okay, if you want to find out the relation, if you are given all the inputs, you can do it. But for that you actually need a computer program, because on a paper you will need so many pages, and also they will make a lot of mistakes. So that's why these computer programs are basically helpful to do these kind of calculations. Okay.